Welcome to this module, and in the previous module what we have seen in the group of modules we have seen how different amplifiers we can generate using the operation amplifier, like what are the applications such as non-inverting amplifier, inverting amplifier, unity follower, summing amplifier, differential amplifier. We have also seen a few filters where we are talking about low pass, high pass, band reject, right. Then we have focused on the data converters which are analog to digital data converters. Now, let us see here what are the digital to analog data converters, and then we will take few examples of how we can design a complete signal conditioning circuit, so that you can interface it with sensors or transducers. Alright. So, when I talk about signal conditioning circuits, the first block is always how to convert the signal to a different domain, and that is left. For example, if I have a sensor which is showing the change in form of resistance, how can I change that form of resistance, and let us say final form is some kind of display, then that resistance has to change it to voltage, that voltage has to be signal conditioning. We have to use it so that we can amplify the voltage, filter out the noise, and then convert it to a digital domain so as to run the microcontroller, and finally you need to display it on some kind of display module. It can be LCD, LED, or whatever the display module may be. And what is the importance of instrument amplifier, whatever the things that we have been learning in the earlier modules, we will be utilizing all those things together, combining it, and then we will make the entire electronic system. So, if you see the screen, what you can see that we have seen the amplifiers, right, filters, data converters. Let us see for today digital to data converter, and then we will follow about the different signal conditioning circuits. So, if you see the data converters, then the basic building block of DAC looks like this, where you have the digital input, right, you have a reference analog voltage, and then you have ground, and then VSS and VDD, which is the supply voltage, and then the output would be analog in the analog domain. So, the basic building block of any DAC architecture, you can use this block to show a block diagram. The first DACs were board level designs built from discrete components, including vacuum tubes as the switching elements. Monolithic DACs began to appear in early 70s. As seen in the figure, the digital word which is here is given to the input, the analog reference voltage is applied with supply voltages for internal circuitry, mostly consisting of operational amplifiers. It can be wired using op amps and discrete resistors, or made as a monolithic chip as is available currently in the market. And finally, we will look at two common DAC configuration, understand why one is better than the other one. So, if you see the DACs, there are two types of DACs. The first type that we are discussing right now is the binary weighted DACs. Now, this is one of the simplest form of digital to analog converter and operational amplifier, which you can see right over here, right, in the summing configuration. If you see the summing amplifier, what was the summing amplifier? That all these voltages were summed together and amplified at the output. So, this is similar to a summing amplifier. So, is used to implement the DAC as well. And weighted resistors that are, you see here the resistor values are changing from R to R, 4R, 2 raised to n minus R, from V1 to Vn. If you have different voltages from V1 to Vn, your weight of the resistors would change, and that there is a reference voltage. If reference voltage is exceeding the value of the voltage, then it will there will be change in the output. We will see how this works. Just let us first understand the circuit in detail. Now, weighted resistors are used to distinguish each bit from the most significant bit to the least significant bit. You always write most significant bit as MSB, where LSB is the least significant bit. Transistor based or other types of switches are used to switch between the V reference and ground. Now, you see here there is a ground, and here there is a V reference. Depending on 1 or 0, you have to change the voltage. We will look at it later, so that we can give different binary inputs, alright, because binary is given in either terms of 1, which is high, or 0 in terms of the ground. The circuit is shown here. Voltages V1 through Vn are either V reference or voltage. You see, if I connect this switch to V reference, then my voltage would be V reference here, right. Or if I connect this switch to ground, right, then what will happen? I will have here 0. So, either it is V reference or 0. depending on the position of the switch. V1 is the most significant bit, and 0 and Vn, which is the nth bit, would be the least significant bit. Okay. So, the expression of the analog output for the weighted binary digital to analog converter is given by V out equals to minus I RF, and what is here I? Minus I would be nothing but the summation of all these voltages. So, V 1 by R 1 plus V 2 by 2 R. So, V 1 by R here, V 2 by 2 R, then V 3 by 4 R and so on until V n by 2 raised to n minus 1 R. So, this is the least significant bit, this is the most significant bit. So, this is a weighted binary DACs. Okay. Now, if I go further, if my RF is R by 2, then the expression would be V out equals to minus I RF equals to minus V 1 by 2 plus V 2 by 4 plus V 3 by 8, so on until V n by 2 raised to n. For a 4 bit converter, it is minus V reference, right. V out equals to minus RF. So, for a 4 bit converter, we will say it is like my V out equals to minus V RF, and then we have 4 bits B 3, B 2, B 1 and B 0. So, it will be like 1 by 2, 1 by 4, 1 by 8 and 1 by 16, right. So, easy to convert your digital signal to analog domain by using this particular DAC. Now, what are the advantages and the limitations of this particular DAC, that is weighted binary DAC? The advantages are that it is extremely simple to construct, the analysis is also simple and the conversion is faster, while some of the limitations are it requires large number of resistors, right, with precision for low value resistors, because you go on reducing the value of resistor, as you can see here, right. There is a V 1 by R, 2 R, 4 R, 2 raised to n. So, the very large value of resistors are required, and extremely precise values are also required. Low switch resistance in the switching transistors is another important point we have to take care of, and then finally, this is not scalable to high bit numbers as the resistor selection and precision gets affected. So, these are some of the limitations of the digital to analog converter. If you move further, then the second kind of DAC is called R to R. Okay. So, the R to R DAC is shown in this particular schematic, right. We can give a number figure 3, it is just a figure, do not worry about it, and is for 4 bit. Each bit corresponds to a switch as shown in the figure. You can see there are 4 bits, right, bit 0, bit 1, bit 2 and bit 3, and each bit corresponds to a switch, right, which you can see here. When the bit is high, right, then what will happen? When the bit is high, the switch is connected to the inverting input. You can see here amplifier, and inverting input of the amplifier is connected to the switches, and also the ground is connected to switches. So, either the switch will be connected to the inverting amplifier or inverting input of the amplifier, or it will be connected to the ground, right. So, assuming the ideal op amp, we will get a configuration as shown here. So, let us say this is figure number 3, right, and this is figure number 4, right. So, for this configuration, the equivalent resistance can be given as. So, if I see you see this is very interesting. If I take this block, okay, if I take this block, now the configuration is very simple, because here is always R to R. You see, let us first understand. See, this is resistor R, then in 2 R, R 2 R, R 2 R, 2 R and 2 R. Why here last is 2 R? We will see about that. So, if you see from the last block, that is from here, and if I have the equivalent circuit of that 2 R, right, these then what will happen? My R equivalent will be 2 R multiplied by 2 R divided by 2 R plus 2 R, and if I do that, my answer would be R, right. So, this is nothing but R resistor R. So, this 2 R and 2 R will be resistor R. Extending this node to V 2, we also taken into account, we can have. So, if I take this V 3 is done, now if I take it to V 2, what will happen for here? It will be R in, it will be like this, R and R. So, it will be sorry, R divided by R plus R. See, if it is just here R, and then there is this equivalent is R, then what will happen? This one is R by R plus R into V 2, which is 1 by 2 of V2, right. It is very interesting and very easy also. The same way you can extend it further to the further nodes. Now, if we extend it to other nodes, we can see V2 equals to half V1, V1 equals to 1 by 2 of V reference, and V out would be minus IR. Now, if I substitute this value, then we have V3 equals to 1 by 8 of V reference, V2 equals to 1 by 4 of V reference, and V1 equals to 1 by 2 of V reference, and expression for V out can be given as minus R into B3 V reference by 2R, B2 V reference by 4R plus B1 V reference by 8R plus B0 V reference by 16R. In another way, if I want to further write it down, I can write down as V out equals to minus V reference, then B3 1 by 2 plus B2 1 by 4 plus B1 1 by 8 plus B0 1 by 16, and so on and so forth. So, for this 4 bit R2R ladder, where we have this B3, B2, B1 and B0 as bits 3, 2, 1 and 0, and if I want to have n number of bits, then the general expression for the R2R ladder would be V out equals to minus V reference summation of I equals from I equal to 1 to n B n minus I into 1 by 2 to the power I. This is the expression for the n number of bits for R2R ladder, and this again the schematic is shown in this particular figure. The advantages and limitations of the R2R DACs are, the first one is that it requires only 2 values of resistors. In case of the weighted binary network, we require very high value of resistors and extremely precise value of resistors, while if you talk about the DACs using R2R ladder, then the advantage would be that it only requires 2 values, either R and 2R, and hence can be made more precise and accurate. Second, the advantage is that does not require high precision resistors, that is the second advantage. The disadvantages of the R2R ladder is the conversion rate is lower as compared to binary weighted digital to analog converter. Okay. So, these are the disadvantages, I can say only disadvantage. Now, let us go to the next module, and the next module would be a basic building blocks for signal conditioning circuits. So, this is really interesting because how we can use or convert our resistors change in resistance value to a different domain, that is our voltage domain. So, like I gave an example, if you have a pressure sensor, and if the pressure sensor is made out of a piezoresistive material, and if we apply a force to or pressure to the resistor, what will happen? The sensor will bend, and the corresponding resistance would change corresponding to the applied force or pressure. So, how can I change this value of resistor to another domain? That is the question, and if you see the slide, what you find out is the Wheatstone bridge for resistive network is one of the answers to our question, that most of the sensors used are resistive in nature, hence the change of resistance should be observed and converted to a low voltage for further processing. Okay. Then the second thing is that this can be done, for the further processing can be done by using either voltage divider or Wheatstone bridge. So, how it can be done? Suppose I have a resistor, right, and I use sensor as another resistor, and this resistance which is R sensor. So, it will be changing, this will be constant R, and let us say if I apply voltage V equals to let us say 5 volts, alright. So, if my R equals to RS when there is no and this sensor is let us say force sensor. So, initially what will happen? I will have R equals to RS, right, R equals to RS. So, here I will have voltage as 2.5 volts, right, because the potential divider network, resistor divider network. When there is no force, so force equals to 0, I will have 2.5 volts. When I change my force, this resistance value would change and this voltage value would change. But if you see that the amount of voltage, that is the total voltage that we apply, supply voltage is 5 volts, but our starting voltage here is 2.5 volts. Thus, the range will be from 2.5 volts onwards, that is almost half of 5 volts. That is why the this kind of resistive divider network is not used, and we go for or we opt for Wheatstone bridge, which is shown here. and mathematically VO is proportional to delta R. Only linearity between sensor output and measure output voltage. Generally Wheatstone bridge circuit, which is right over here, you can see here there are 4 resistors and the fourth resistor is your R sensor. You kept it like this because your sensor will change the resistance value, and that is why R plus delta R. Generally Wheatstone bridge circuits are preferably for measurement of the resistance. For an accurate measurement of a Wheatstone bridge circuit is used. The measured circuit is shown here, and the drawbacks of this are offset voltage, offset output voltage for no loading condition is a main drawback, right. That is the first thing. Second thing is temperature variation needs to be compensated with additional circuit, and finally the wired length will also add into resistance value, which needs to be compensated. So, you see the temperature, if the temperature of the resistor changes, how it is compensated, that is the drawback, and finally the wire length will also add the resistance values to the for the compensation. Okay. So, that is another thing that we need to take care. Yeah, so we were looking at the drawbacks, and like I said, there are few drawbacks, particularly output offset voltage for no loading condition. That means that even when the resistors are all in the initial stage and there is no change in the resistance, because let us say again this resistance is our force sensor, right. So, we are not applying any force, then all the resistance values are same, still you will find some kind of offset voltage at the output, and that offset voltage we need to null it. That is one drawback. Second thing is that with respect to temperature the things would change, and finally the wire length that we already discussed. So, if we further go, the basic building for singular conducting circuits, when we talk about the constant voltage source, so that means the Wheatstone bridge for resistive sensors with constant voltage source and constant current source, how it will differ, and let us look at this. So, if you see lot of things we have merged in one single slide, very informative slide. So, if you see here we have voltage V out, which is here, right. This, if you see this particular configuration where only one resistor is changing, right, then we have VB by 4 delta R by R plus delta R by 2, and here the linearity error would be kind of 0.5 percent, and then you can also see further that if I have two resistors value which are potential dividers, sorry, which are potentiometers, then I will have my output voltage as VB by 2 into delta R by R plus delta R by 2. Similarly, if I use this particular configuration, then here when one resistor is changing, it is increasing the resistance, the second resistor will be decreasing the resistance. This will be the case of a cantilever beam where you have the resistor one in the bottom and one in the top piezo resistor. When you apply a voltage, the cantilever beam will move will bend, and there will be compressive stress and there will be tensile stress, and because of which there will be change in resistance, one will be increasing, one will be decreasing. The final one is if you have all 4 resistors in this particular format with a constant voltage source, then we have value VB into delta R by R. So, these are the configuration for single varying element to all element which are in varying nature. So, if the figure shows the output voltage and linearity error for constant voltages, these are all output voltage and linearity error. You can see linearity error in case of this bridge as well as this bridge is 0, right. So, preferably we should go for 2 element varying or all element varying bridge configuration. When you talk about constant current sources, then you can see here for the first configuration we have voltage equals to IB R by 4 into delta R by R plus delta R by 4, where you have the second configuration which is similar to this one, right. We have IB by 2 into delta R. Now, here the output voltage will be different because now we are using a constant current source. Finally, we have the 2 varying element, we have IB by 2 delta R, and finally we have all varying element, then we have IB into delta R, right. So, the output voltage and linearity error for constant drive bridge circuits configurations are shown here. Here the linearity error is 0.25, 0, 0 and 0, right. So, the here for the constant voltage source we can see that linearity error is major bottleneck with this configuration, right. While in the case of constant current source, what we find is that selection of IB is trade off between full scale between full scale value considering driver output voltage and measurable output change for small change in resistance, right. So, that is another thing that we need to take care of when we are designing the signal conditioning circuits, right. So, let me end my this module here, and I will continue with the further signal conditioning circuits in my next module. Till then, just go through what we have learned, and I will catch you in the next module with more information about how to the instrumentation amplifier can be used in the case of the signal conditioning circuits. So, till then you take care. I will see you in the next module. Bye.